Our speaker is Dr. Kris Stanek from OSU, and his areas of research are supernovae, gamma ray bursts, galactic structure, and time domain astrophysics. And the title of this presentation for tonight is All-Star Automated Survey for Supernovae, Big Science with Little Telescopes. So I would like to introduce Dr. Stanek.
Thank you. Thank you for inviting me. I will. We're being recorded, so I will be careful not to say anything embarrassing. The idea for the talk today is that I want to tell you what happens and when you observe the entire sky every night, obviously not from Columbus, and how you do it, and then once you do it, and you do it for many years, then it turns out you discover a lot of things. So that's basically my talk. And there's lots of words which you shouldn't read, but the idea is that the sky is very big. That's a basic question we always ask our graduate students, how big is the sky is in square degrees. That's a very simple calculation, 4 pi steradians, that everybody knows that, but then in terms of steradian, it's just radian by radian, and so if you do that, it turns out the sky is 41,000 square degrees. At any given time, roughly 1/4 of that is not observable from the ground because it's what we call behind the sun. And so if you want to observe the whole sky from the ground, you still have to cover 30,000 square degrees every night, and you need some resolution to do it. And so this, despite what people might think, it's not something we have done until this project started roughly 10 years ago. So until we have started doing that, and really it was more like 8 years ago, the entire sky was not observed every night by astronomers. It might be observed by the military, but they don't share the data with us, for some reason. I don't actually know if they do it. They have similar issues. As I described, it's just the data rate and the ability to do it really is the computers and the computer technology. We are able to do it 10 years ago, but definitely not 20. And so if you want to observe the whole sky, just one image with 1 arcsecond resolution, which is pretty good. It's not Hubble or JWST, but it's pretty good. That one image would be 1 terabyte. That used to be a terrifying amount of data. When I started my postdoc in 1996, I bought a 9 gigabyte disk for $2,000. Of course, now you can buy the many terabytes of data for much less money. So that's the one thing that has happened. The other thing that has happened is internet is much better. We can actually not just take the data, which is kind of easy. Everybody can take images. We can transfer the data and reduce the data in real time, pretty much in real time, such that there's roughly maybe 1 hour delay between taking data, let's say in Chile, I would describe where the telescopes are, and us actually knowing more or less what's in the data. And so, but still, to be able to actually do it, and again, we are the only project, there's another one now, but for many years we were the only project that actually was able to do it. We are able to do it by having large pixels. So in fact, we do not observe with 1 arcsecond resolution. We use telephoto lenses, Nikon very nice lenses. And so our resolution is 1 pixel is roughly 8 arcseconds. So now you cut down by a factor of 60. So for us, one image of the sky is 1 terabyte divided by 60, which does reduce the data rate quite a bit. The scientific goal, why you want to do it? Well, you want to do it because the sky is there, and you want to observe it in basically unbiased way. So JWST is great, Hubble Space Telescope is great, but they point somewhere. You have to write a proposal. We have done it many times. 1 in 10 proposals will be selected. You get your data, then some months, a few weeks later, you actually get the data, and then the data becomes public 1 year later. Here, we want to observe the entire sky every night, and then reduce the data in real time and see what happens. Then we want to, because we use these relatively small telescopes, as I will show you, they're only 14 centimeters in diameter. We don't go very deep. We only go to 18th magnitude. But that's still plenty good. Turns out there's roughly 100 million stars which are brighter than 18th magnitude in the sky. So we'll be able to record brightness of roughly 100 million objects. And if something is normally fainter but becomes brighter temporally, which many objects do, then we'll also be able to see it. Because we don't build, there's a very strong instrument lab at OSU, but that's not me or my collaborators. We didn't want to build the telescopes. We have no interest in the instrumentation. We just wanted to buy the telescopes, buy the CCDs. We paid somebody, which was the tricky part, but nevertheless, we paid somebody to build these for us and run them for us, and so we do the rest. We reduce the data, analyze the data, and most importantly, get the science out of that and write papers and become famous. Not really. The original scientific motivation was that, again, supernova searches traditionally were operating in the mode where you take a telescope, 0.5 meter, 1 meter, you point at the galaxy. That doesn't sound crazy. That's where the supernovae are, but it turns out we learned earlier this century, namely roughly in 20 years ago, that there are many supernovae in what we call dwarf galaxies. And these dwarf galaxies, turns out, not only have supernovae, but these supernovae are actually different than the supernovae we normally find in big galaxies. So original motivation for the project was, let's construct an unbiased survey looking for supernovae. But it turns out that, as you will see from my talk, very little of my talk will be actually about supernovae, because once you start observing the whole sky, there's just a lot of other things that show up. And we were very good about keeping our eyes open to that science. The other thing we do a lot is because we have these unique data, and we have obtained by now roughly $5 million for private foundations to actually run this project, we promised them all along that we'll make a lot of data public. So it's not just us using the data, but anybody in the world, literally anybody in the world with internet access, can get to our data and use these data. And so that's a very important aspect of this project. It turns out that the impact of the project, if we were just writing papers compared to what other people do, we would be only just a few percent. So the impact of all the other people using our data for their research is at least 20 times bigger than it would be just our team doing that. So this started with just few people at OSU. It was myself, Kris, and then Ben Shapi, who is now a professor in Hawaii. He was a graduate student. Very brave, actually, because the project maybe wouldn't work, but he stuck it out. And a big part of him now being a tenured professor at one of the best universities in astronomy in the world is that he was part of this project. And all the people in gold here, they were at some point at OSU. So we started with 4 or 5 people and slowly built to a team of roughly 40 people at 20 different institutions by building these long-term collaborations with our students who then succeed and become Hubble Fellows and then become faculty and they go somewhere else. And we are on 4 different continents by now. So again, this wasn't just growth in terms of putting telescopes on different observatories, but also probably more important, the growth in terms of building a network of people who will actually extract science from this survey. So these are our telescopes. These are 4 Nikon lenses. These are just the scatter light. There's a word for it in English, which I forget. These very nice mount. We didn't build them. We paid for them. They're quite pricey, $200,000 each. The CCDs are $40K, and the lenses are $10K. I'm just mentioning the hardware itself is maybe not that expensive. It was probably about $1 million so far. But we also have to pay roughly $500,000 a year to actually run it, which is relative for 5 different mounts. Is actually not at 4 different sites. It's not that expensive, but it's a constant amount of money we have to spend. And so these are 14 centimeter lenses. If you combine this with this 8 arc seconds I mentioned, each of these telescopes is 4.5 by 4.5 square degrees on the side. So that's a huge field of view right there, and we have 20 of these. And then we take a 90-second exposure, shift the telescope a little bit, take another 90-second exposure, shift the telescope a little bit, and take a third 90-second exposure pretty much at the same point, because we found out that we reduced the number of false positives by an order of thousands if we do that. If we would just take 1 image per field, we would be swarmed by what we call false positive, hot pixels, cosmic rays, whatever. These days, even these Starlink satellites, they don't bother us too much. They bother us, but we can kind of remove them because by the time you take a second exposure, they're gone. And this is a technical point, but we switched at some point to what's called the G-band filter, which is this Sloan survey filter, which is bluer than traditional V-band filter. It actually made our survey deeper by 1 magnitude. So that effectively made our telescopes bigger for a price of just a few $100s. I wish we did it initially, but we didn't. So with these 20 telescopes, if all the sites are clear, we can take 6,000 images per night. So if you do the math, that's 40,000 square degrees. And that's the interesting number because the area of the sky that you can actually need to observe is roughly 30,000. So even if one of the sites is maybe not perfect that night, we can still observe the whole sky every night. Sometimes, unfortunately, even at the beautiful sites that we have, which I will describe, sometimes all of them are cloudy, but that doesn't happen very often. By now, we have taken 10 million science images. Each of them is 8 megabytes. And we keep copy, and then we have a lot of data products, because again, the data are actually public, and anybody can access it, including all of our previous data. Not the images, but you can access various data products. So all of these images are sitting on a disk, on many disks, on many servers, and we can access them at any time. We take about 2 million images per year. So the sites were originally, we started in Hawaii, and then we deployed in Chile. The idea was to have telescopes on both hemispheres, because if you want to observe the whole sky, you have to be on both hemispheres. And then we obtained a large grant from the Moore Foundation, and that allowed us to deploy more telescopes in South Africa, Texas, and then also we deployed another telescope in Chile because this is our best site. So there, effectively, we're getting more images per night because they're just there are just not very many cloudy nights. So here's one of our images. This is a galaxy I'm sure you heard about. It's called M33. Doesn't look very large because, again, we have very large field of view. This is a full moon here. And here is the upcoming field of view of the it used to be called LSST, now it's called Vera Rubin telescope, which will cover large chunks of the sky with a 8-meter telescope. But actually, the price they pay is their field of view. They brag how big their field of view, but it's actually quite small. So they'll be only able to observe roughly 3,000 square degrees per night, which is a lot. But they will go to 26 magnitude. So they will observe billions of objects every night. But a lot of these objects will not be, you cannot observe them. If you discover something interesting, there is no other telescope that can actually observe it because that telescope is already so big. Anything we discover, because we use 14-centimeter telescopes, anybody in the world, many of you have bigger telescopes than we do, I'm assuming, because 14 centimeters is not very large. And so as I will describe, the follow-up, when we discover something and then announce it, when people observe these objects, that's the crucial part of science, is that not just finding something in the sky, that's easy, once you know how to do it, but then follow-up is actually a crucial part of the scientific process. All right, so here's our sky coverage. Each point on the sky, I just grabbed this yesterday, has at least 2,000 images by now from our project. And some points of the sky have 8,000. At some point, for whatever reason, our scheduler decided it was observing the same field. We had like 5,000 images in 1 year. We still don't know why. It might be artificial intelligence, but probably just a glitch in our software. But these data, any point of the sky, if you ask me for a light curve of a star, if it's not too bright, because it's saturated, we saturate roughly at 10th magnitude. So if you have a star between 10th magnitude and 18th magnitude, I can give you at least 2,000 data points, but maybe 8,000 data points for that star. So a lot of people are using our data because if you have 100 stars on the sky that you want 10 years of data for, and you wanted to observe yourself, you would go crazy. Or you can just go to our database and get the data and write the paper back. So that's one of the, I think, probably the biggest strength of the project, that we allow other people access to our data. So how do you do it with these large pixels? Well, if you go to Large Magellan Cloud or Galactic Center or anywhere, it turns out that's a very poor resolution. So using traditional software, you will not be able to see anything. But there is this magical software, which was roughly developed 20 years ago, called image subtraction, where you take a bunch of images, you co-ed them, you make the reference image, which is a deeper image made from your best images. Then you take new image, that's an image from last night. Then I digitally match them to the same reference, and then I just subtract them. So the analogy is, imagine I took a picture of the audience, and then somebody left, one person, and then I took another picture. Normally, the normal software, you would have to count everybody, and then you would deduce that one person is missing. If I do image subtraction, and nobody moved in the meantime, I subtract the two images, and the fact that the person left it's immediately obvious. There is a hole in the image. Or if a person appeared, there will be an extra person. Everybody else disappears. So that's what happens in this image. When we do image subtraction electronically, LMC disappears, but if there is a new star, a known star has done something, exploded, or a star disappears, we will see that as well. So we'll see a hole in the image, and we'll see extra light in the image if there is some new light. So the whole idea of how this project works, because of the image subtraction, we actually have significantly better resolution even in crowded images. If a supernova occurs in the middle of faraway galaxy, relatively far away, relatively nearby, but still far away, we'll still see it because we can subtract the galaxy and we'll just see the extra light. So we built this transient detection pipeline, which is still clunky because we are not programmers, but we know what we want, so this was built by us. And it works because we, as astronomers, we are asking it to do things that we know what to do. And so here's an example of, you won't even believe me, but there is an actual detection of an object here. It would show up better if it was a bit darker, but that's okay. And this turns out that once we observed, no, but it's okay because but all right, we want to do this? We want to, okay. Anyway, this turns out once we took follow-up data, this was the most powerful supernova ever discovered. Not the brightest, because brightest, as it appears to us, obviously this is not a very bright object, because it's far away. But once we determined how far away it was redshift 0.2, it turns out to be the most powerful supernova ever discovered. And it barely showed up in our data, but because it showed up in our data multiple times, it eventually would trigger on it and followed up. Sometimes these detections are much less subtle. Here is a nova in our own galaxy. So here is a thermonuclear explosion from a white dwarf in our own galaxy. These objects brightened by a factor of 10 magnitudes, so it's a factor of at least 10,000 or more. So normally there's a white dwarf with an accretion disk and suddenly becomes relatively bright. Some of these are naked eye, very few. This was maybe 11 magnitude. But this was from June this year when we have the discovery. And this is now in the range of any amateur astronomer, or as I call them, unpaid professional astronomers, can observe this with their telescope and even take spectra. In fact, there is a lot of effort in amateur astronomy to do spectroscopy now, not just take images. So the follow-up facilities are very important. I'm getting to the science, but I just want to explain how the science, how the data chain works here. ASAS-SN observes the whole sky. We take the data, move them by internet to SU. We don't have supercomputers, but we have our own dedicated servers that reduce the data. They produce these GIF images. I actually look at a lot of them, but we also have automated pipeline alert system as well. And then we say there's something new, and then we decide should we use some bigger telescope to take a spectrum. And if it's really interesting that we have used Hubble, we have used all the space telescopes except JWST yet, but we'll use it as well to take follow-up data and then write papers. And then we have collaborations with people around the globe, including a lot of people over the years with and Isaac Cruz here as well. So we have observed with him for many years. So our own team, which again grew quite a bit over the years, writes roughly 20 papers a year, which is a pretty good number. We have discovered roughly 1,300 supernovae, and because we try to find them in a very unbiased way, we find them in big galaxies, but we find them in small galaxies, and in a few cases, we actually do not have a host galaxy. We have a supernova, but there is no host galaxy there, which is unusual, but actually very interesting. We found roughly 20 so-called tidal disruption events, which are very rare, and until we started discovering them, well, not a lot, maybe 1 or 2 a year, but we really open up a new field of astrophysics with our project, that there's now a good sample of these tidal disruption events. I will talk about them a little bit more and why we care. We have new discoveries, 300,000 variable stars. And all of them are brighter by definition than 17, 18 magnitude. And so, but we also observed another 500,000 variable stars with our data, and for at least 100,000 of them, we actually changed their classification because the existing data was poor and our data was much better. So we could, as we were finding new variable stars, we were actually reclassifying a lot of non-variable stars, which turns out in many cases were just discovered with maybe 2,000 images, but we have hundreds and now thousands of images. We discover so-called cataclysmic variable one every day, still. And here's just accretion disk around a white dwarf, which goes dwarfs with accretion disks, that there is a new discovery of new object by our project every night on average. So we have discovered roughly through 2,000 of them. We see a lot of large M-dwarfs flare. I will talk about them. We also see all the black holes with accretion disks are variable, quasars, or what we call active galactic nuclei. But we have found some really new science here as well, because again, we keep our eyes open, and when something shows up, we are very interested to see what's happening. We have discovered roughly 20 classical novae in our own galaxy. Few of them actually almost naked eye. I think one or two were naked eye objects. And then 2 comets, and then was a very exciting asteroid in 2018 that almost hit us. It was called 2019 OK. I'm not making this up. And that was exciting as well. Very important aspect of the project, and something I'm very proud of because I really enjoy working with students, graduate students, is that they come to OSU. We get some of the best students in the world. Again, I'm not exaggerating. And they're able to use these unique data to produce unique science. And then they move on and eventually become faculty somewhere else. Not all of them, but many of them. And they obviously still like us because we're still collaborating with some of them down to this point. So we had Tarinder Jayasinghe, who is originally from Sri Lanka. He came here for 5 years. He never has seen snow before, but he got used to it. Of course, he after 5 years, he now moved to Berkeley with a Hubble Fellow, which is one of the best so-called postdocs in astronomy. And as you can see at this list, we have quite a few Hubble Fellows over the year. The Ben Shapi, who I mentioned, also left as a Hubble Fellow to Carnegie, and now he's a faculty in Hawaii. But the idea is that we have few older people. I'm not old yet, but I'm getting there, but older people. But we train new people, and then one of the students of Ben Shapi has now came to OSU as a postdoctoral fellow here. So we again we keep these networks open, and that's very much an important part of the project. All right, I'm kind of going slow, but let's get to science. Let's start with variable stars. So when Tarinder came here 5 years ago, I said, you know, a lot of amateur astronomers work on variable stars because they're actually interesting, but a lot of professional astronomers in the US don't work on variable stars. It's kind of more seen as a field, much more a field, a professional field in Europe. And I said, well, if we observe the whole sky and we have hundreds of data points and now thousands of data points, you can certainly write some papers that nobody else can write. But of course, it's not going to be easy. You have to be able to process almost a petabyte of data now, take these light curves, reclassify them, and so on. But unlike, I don't know anything about machine learning, but the young people these days, they know about machine learning. So he, even as a very young graduate student, he said, we can do that better than people have done before because we have better data, but we have machine learning as well. So he was able to discover 200,000 variable stars, and his very first paper already has 200 citations, which is in astronomy is quite a bit. So that's very significant work, because again, when you produce something new, people will appreciate it. So here is a sky map of these 200,000 variable star discoveries. And then a few years later, with another student, he was actually undergrad at OSU, he's now a graduate student in Arizona. We have taken the new data because we have switched the filters, which goes deeper, and we were able to find another 120,000 new variable stars. We could probably find more, but again, this is a lot of work at any given time. So we haven't done it many times, but we were able to do it twice so far. We have found not just few or a dozen or 100, we have found 100 or 200,000 new variable stars and classified them and made the data public, which is again important. And so another aspect of this is that particularly interesting class of stars, which are known for a very long time, are eclipsing binaries. It turns out eclipsing binaries are especially valuable because if you can measure their radii and you can take radial velocities using spectrographs, you can actually measure masses of stars. And so if you take detached eclipsing binaries, you can actually do a lot of sort of basic astrophysics, but which is crucial for better understanding of stars. So another graduate student I'm working with now has produced a value-added catalog of 30,000 detached eclipsing binaries, which is roughly factor of 10 more than has ever been done before. Because again, we have better data than anybody else, but now we have also very sharp young people who know what to do with computers. And I mean, I'm pretty good at computers, but they're more, they grew up with them. Here's a very interesting object, a so-called heartbeat star. I won't spend much more time on it, but this is a case where there are two stars in a very eccentric system, and when one star gets closer to the other star, the whole star starts to oscillate like a heartbeat. And so you see this big variation here, but then you see these little variations as well. And so we wrote a paper about that. Just an example of sometimes we write catalogs of variable stars, but sometimes we also write a paper about individual variable star if it's particularly interesting. M-dwarf flares, if you ask how many stars there are in our galaxy, the answer is 100 billion, roughly. Half of them or more are M-dwarfs. These are stars with 0.2 to maybe 0.5 solar masses. There's just lots of M-dwarfs out there. And M-dwarfs live forever, and M-dwarf can live up to 1 trillion years. So the sun will live only for 10 billion years. M-dwarfs just sitting there burning fuel very slowly. And so there's lots of them, and they live forever. But now and then, they have very strong magnetic fields, and there's a lot of energy accumulating in the magnetic field. So an M-dwarf can brighten in optical light by a factor of 1,000 or 10,000. So very quickly, within one of the very first papers we wrote was this one. So we started in 2011, but really we started reducing data in 2013. And we have seen a 9 magnitude M-dwarf flare. So the star has brightened by a factor of 4,000 in optical light. Now imagine if the sun did that, well, we wouldn't be here to discuss this event because that would kill us. But these are very short-lasting events. So the reason we caught it is because, as you remember, we take 3 images consecutively. So during that time, that star actually brightened by another 2 magnitudes and then started decaying. And as it happened, we got lucky. We took another image of that field, and a few hours later, it was almost gone. But this was the biggest M-dwarf flare ever seen. And that releases as much energy as the whole star releases for 3 months. So these are very significant events. And the M-dwarf flares we have discovered, there was another one which is 11 magnitudes, which is now a factor of 25,000 brightening, which was a few years later, are the biggest M-dwarf flare ever seen. Because these don't happen very often for any given M-dwarf, but there are lots of M-dwarfs, and we are observing the sky all the time. And so we have seen the biggest M-dwarf flares ever discovered. We don't write papers about it anymore, but early in the project, when we first started seeing these things, it was really spectacular that such things even happen. I mentioned cataclysmic variables, which are, you have the donor star. This is low mass star, let's say 0.5 solar masses, slightly evolved. Here used to be several solar mass star, but now there's a white dwarf, so let's say this is 0.6 solar masses or so, and there's an accretion disk. And what happens in any accretion disk in the universe is not stable. So it's stable overall. The stuff will fall on the object slowly. It's basically, at any given time, it's in the orbit around the object, black hole, neutron star, white dwarf. But there are instabilities in these accretion disks. And one of the instability, which is seen a lot in cataclysmic variables, is that the accretion rate is low and suddenly becomes much higher. So this whole disk can brighten by a factor of almost 10,000. The biggest number you ever see is 9 magnitudes, which is a factor of 4,000. So again, normally we wouldn't even see the star because it's too faint for us, but if it brightens by 9 magnitudes, it suddenly becomes a very easily observable object. And so again, we are discovering one new cataclysmic variable almost every night. And some of them are quite spectacular. This was a very interesting object because, first of all, was a new nova, which is a new nova, which was right here. And as it happens, this is towards the Carina Nebula, so somewhere in there, it's the famous star Eta Carina, but that's too bright for us, so that actually saturates in our data. But in this case, there was one of these microsatellites, nanosatellites, whatever they're called bright, staring at the star here, but our nova went off right next to it in their field of view. Now, number of times when I gave this talk, people say, well, you get lucky. I said, if you consistently get lucky, it means you're doing something right. And we've been getting lucky a lot, as I will show you. So again, yes, we got lucky, but so so this is not our data, this is follow-up data from this smaller satellite. They're even smaller, but they're in space, so they can stare at the star for months. And then here, you have a light curve from gamma rays, a Fermi satellite. And so the importance of that paper, which was actually published in Nature by Elias Aidi, who's also a Hubble fellow working with our project, is that if you look at the gamma rays and you look at optical light, these peaks match. So our kind of naive, old-fashioned picture of a nova where you accumulate stuff on the surface of white dwarf, and at some point there's an explosion, does not reproduce this picture. There's some other physics here which is responsible for producing peaks in optical light and in gamma rays. So again, this old picture of novae, which I grew up with as a student 20 years ago, and even 10 years ago, is now completely being changed, not just because of our observations, but observations from satellites. It's actually important that we have optical and gamma rays and other wavelengths as well, so we can cover different parts of the spectrum and understand the astrophysics better. One of the objects, another ASAS-SN EY, here was first seen by us, then a few days later was seen by an Xray satellite, and so was so-called Xray Nova. This is when the accretion disk around the stellar mass black holes activates, and suddenly these things go crazy. And this thing has now almost 500,000 observations uploaded to AVSO website. Every time I actually try to produce the full light curve, it crashes on me because their server cannot handle it. So you can do it maybe last month or last few months, but their own plotting software doesn't actually handle the light curve for this object. But the reason people observe it so much is that things, accretion disk around the black hole, when it's active, can change on the timescale of minutes or sometimes even seconds. So people were literally observing this thing with a cadence of 1 second or even faster. And all of these data are from amateur astronomers, the 500,000 observations here. But many other objects with ASAS-SN names have many thousands of observations. So again, we found them, we announced them, but then people spend months observing them and then writing papers about it. Okay, I said we started a project to observe supernovae, and which we did, so I will describe some of that. Here is an artist's conception for this most powerful supernova ever discovered called ASAS-SN 15LH. And so if this thing happened in our Milky Way, it would be almost as bright as the full moon for 5 months. Not just Betelgeuse distance, anywhere in the Milky Way, unless you're behind a lot of dust. This thing was 20 times brighter than the entire Milky Way galaxy for months. But of course it was far away, so it wasn't as bright to us. And so we have discovered this thing. There is quite a bit of story there, but I don't have time to describe it. It took us a month to really confirm that it was so powerful. And then we've taken a lot of data for it. As you can see on this plot, a typical supernova. This is the supernova in the Large Magellanin Cloud, 9087A. This is a typical type 1a supernova, which is what happens when you burn the white dwarf in a dramatic event. These are the most common type of supernovae that we discover. Most of the supernovae we discover are type 1a supernovae. This event was 100 times more powerful. And so this is Milky Way luminosity. It was outshining the host galaxy for months and produced a total amount of energy, which is actually still people argue. It produced so much energy that many people said it couldn't possibly be a supernova, and they actually wanted to explain it with different physics. But I think they're fools. I mean, I'm sorry. I should have said it. No, they're not fools. Disagreement is good in science. Another thing that we got very lucky, but again, we keep getting lucky, is that Kepler satellite, which you remember was designed to look for planets and has discovered many, also had the project that they would select, as they were looking for planets, they also would select stamps for some galaxies, and they were hoping for a supernova in one of these galaxies. So it wasn't an all-sky mission, but it was a pointed mission. And we were, again, lucky to find the best. We found a supernova called ASAS-SN 18BT. So here's our data. But the Kepler satellite at the same time was staring at that field. So this line here, which looks like a model, is actual data for supernova. It's the best supernova light curve ever obtained in terms of precision. It turns out it was just yet another type 1a supernova. They're interesting, but I'm kind of jaded by now about type 1a supernovae. So I just see another type 1a supernovae. But there were several different papers written by several different groups about just this one event because of that light curve. And then there's another satellite called Tess, which is they use even smaller telescopes than ours. They're only 10 centimeter, but they're in space. And they have this strategy of observing a stripe on the sky, which is 26 degrees on the side times 26 times 26 times 26 times 26. So it's roughly 100 degrees by 26 degrees. So it's a pretty good chunk of the sky. And they stare at that part of the sky for a month with a cadence of every few minutes. So we obviously, and Ben Shapi was still a graduate student here when somebody came and gave a talk about this Tess satellite. And he said, well, Tess satellite has this unusual orbit that it goes almost to the moon and then comes back and can only download the data twice per orbit. So basically every 2 weeks. So it comes close, downloads the data, goes away, and downloads the data. But if we are observing, we know where the Tess satellite points, so we are observing that field with ASAS-SN. We can discover something in the field of view before Tess even downloads the data. And they don't even make the data public until a few months later. So this way we can find something, name it ASAS-SN, which is great, take more data with bigger telescopes, and then when the Tess data comes, we can analyze the data and see what shows up. And so I had a graduate student, Patrick Valelli, who turns out we had dozens of the supernovae. So here you don't need to get as lucky as with Kepler because the field of view of Tess is bigger. And we have found several dozens of supernovae now. These light curves are not as good as the previous one, but now you can do statistics, and we are learning some interesting things about type 2 supernovae, but also type 1a supernovae. Okay, so let me go to black holes. I am not going in any depth here, but I'm always happy to answer questions if you have any questions after the talk or during the talk. And so stellar mass black holes are very interesting. The traditional method, the rule of thumb, which is that there is 100 billion stars in the galaxy, there is 10 billion white dwarfs, there's 1 billion neutron stars, and there's 100 million stellar mass black holes. That's just if you run your code for stellar evolution, that's the numbers you get. Of these 100 million black holes, 90 million of them are just floating through space. So you cannot see them. There's nothing to accrete. There's just a black hole with 5, 10 solar masses going through space. Very hard to discover. But 10 million of them are in binaries because there are lots of binaries. So if you have a black hole stellar mass in a binary, the traditional way to discover it was if this star is donating mass through accretion disk on a black hole, you have an accretion disk which is extremely hot, and it's an X-ray source. So back already the first stellar mass black hole binaries, Cygnus X3 and others were discovered in the 60s when the first X-ray satellites were launched. But it turns out basically we have discovered so far less than 50 of these because these are not very common. They don't last very long because as you accrete, eventually you exhaust the material, so they don't last forever. And often they are in quiescence, what we call quiescence. So this accretion disk, if it's not in high state, is actually not visible in X-rays. So people have been discovering roughly one new one per year. This ASAS-SN 18EY was one of the new X-ray black hole, basically, with a donor star. But there should be another millions of black holes in binaries which are not accreting. So how do you find them? Well, you find them by looking at the companion star and observing the companion star. And if the companion star, for example, is moving too fast, because it has to move quickly because there is a lot of mass in the system, that means there's a black hole there. But it turns out it's a very complicated thing to do, and we're just started scratching the surface on this science. So the X-ray black holes, if you will, we find them under the lamppost because that's the easiest thing, and that's actually perfectly fine. But now we want to find the other black holes which are not under the lamppost, and it turns out that's actually very difficult. So how we use ASAS-SN for that? Here is the other way we find black holes, of course, is when they merge and they produce a LIGO event. So this science has only opened up since, I think, 2015. That's great, but all of these are far away, somewhere in the universe. We don't know exactly where, and all we know is that two stellar mass black holes merged and produced another black hole, which is awesome, but we have no idea about the statistics, or even none of these are in our galaxy, of course. They're all very far away. So we want to find black holes before they merge, or we want to find black hole plus ordinary star and see how these populations behave. And so this yellow annoying animation is the one stellar mass black hole we actually have found so far. And I will not go through a lot of detail here, but we select the radial velocity data. So this is the velocity data from Sloan survey, which has been going on now for more than 20 years. They also make a lot of data public. So we look at their data. This is done by Todd Thompson, which I believe he probably gave a talk here a few months ago, I was told. And so we select our V data, we match it to ASAS-SN data. Long story short, we're pretty sure, although there are some naysayers, that this is an example of a black hole plus a giant star companion. And it's quiescent, so there's no mass transfer, so there's no X-rays. There's no accretion disk. One way you could look for black holes, if you have a normal star, regular star, next to a black hole, the tidal forces from the black hole will deform the star, and you should see this deformation in the light curve. It's so-called elliptical variation. So another project that Dom Rowan did when he was a first-year graduate student in his first year here during COVID, so I didn't even see him in person, and we were working on this paper, is to look through our data and select a sample of stars that could possibly have a black hole companion. We have that in the journey. So these were stellar mass black holes, were produced by stellar evolution. You start with 30 solar mass star, and maybe you have 7 solar mass black hole in that. But nature also figured out how to make supermassive black holes. We haven't figured out how nature does it, but there are black holes with our own galaxy has a 4 million solar mass black hole in the center. Andromeda has 30 million solar mass black hole. And there are some black holes which are more than billion solar masses in the centers of the galaxy, always in the centers. Every massive galaxy has a central supermassive black hole, if it has a bulge. M33 does not have a bulge, and we don't think there is a black hole. So somehow when you make a bulge or elliptical galaxy, you also make a supermassive black hole. By now, the vast majority, when these black holes were growing, they were all X-ray sources, they were all quasars. But that was at redshift 3. Universe was much more interesting at redshift 3, really. It was smaller, so it was easier to see. And also, there will be naked eye quasars on the sky. Of course, Earth wasn't formed yet, so there is a detail here. But the universe was quite something at 10 billion years ago. But so these quasars are no longer quasars because these black holes have formed. There's no accretion. They're just sitting there in the middle of a galaxy. So locally, when we look at the galaxies around us, maybe only 1% of the galaxies have what we call active galactic nucleus, AGN. 99% of the galaxies, our Milky Way, our black hole is basically dormant. There's very little activity, but it's basically nothing is happening. It still has the mass. So another way to look at this 99% of black holes which are normally not active is to wait for them to do something, and then we'll observe the black hole in action. So one of the things that happens is that if a star happens to come too close to the central black hole, it will become disrupted, and it will form an accretion disk, which will last for a few months. But during that time, you basically have a quasar, but it will have a limited lifetime, because the supply of the material is not coming, some gas coming from the galaxy, but this one star comes too close, becomes disrupted, like in this picture, and forms what we call a tidal disruption event. These things have been hypothesized. Some of them were discovered before ASAS-SN. What we started doing, we started finding them, because we have small telescopes, we started finding them in relatively nearby galaxies, and they're bright, because otherwise we wouldn't see them. So the first few, which we have discovered in 2014, have been observed. There are hundreds of papers written about them by now, because the data was just so good, because they were the best, the brightest, and the nearest to us. So of course we could use Chandra, we could use every X-ray satellite, we could use optical telescopes and so on.
Along those lines, what's the limiting magnitude to assess?
18, but 17 really is more for discovery. So we can discover things at 18, but some of these things were 14th magnitude and so on. Anyway, I won't go too much detail into it, but we've discovered some very interesting things about tidal disruption events that we just didn't have the data before. And again, ASAS-SN just provides the trigger, and then we have a team, and we announce them so other people can observe them as well. From the very beginning, we always said we were not going to sit on our discoveries. Astronomy is just too beautiful and publicly funded. So we shouldn't just, we discover something, we should announce it to other people, because we might not figure it out unless other people figure it out. And I think this works very well for us. That's why I think that the private foundation which are funding us also like this approach, and they're basically paying for us to run, because it does not run for free. So we got lucky again with this one. This is ASAS-SN 19BT. We had this idea that wherever this Tess satellite is pointing, we're observing the whole sky, but we will be observing the region even more frequently. And there was a tidal disruption event in the field of view of Tess, which, again, we didn't get super lucky, but what we got really lucky is there is a small part of the sky where the Tess is not just scanning for 4 weeks, it's where it's called continuous viewing zone. One of these chips, it has 4 chips, one of these chips always looks at one spot on the sky. And our TD happened to be in that spot. And so in this case, we don't just get 4 weeks of data, we get months of data. And the Tess people, and this is a satellite designed to look for planets, they love us. They really like the idea that the satellite, which is designed to look for planets, is also making many cool discoveries. So when NASA had the Black Hole Week, this was one of their featured events. But this one is the best, probably the best discovery we have made. It's ASAS-SN 14KO. I don't expect you to remember the names. And the story is that 14KO means we have found it in 2014. It just seems that way. And at the time we took a spectrum, we thought it was some unusual kind of supernova, and then we didn't do anything about it. We cannot write papers about all the supernovae. We have discovered more than 1,000. So we named it, we released it, and then we forgot about it. And then a few years later, in 2020, Anna Payne, who is a graduate student in Hawaii, she's working with Ben Shapi, she had a project they use ASAS-SN data to get light curves of many centers of galaxies. And she noticed that one of these galaxies had a repeating event every 110 days or so. And then she realized it was already found by us back in 2014, but we didn't realize that this thing was repeating. Quasars do not repeat. Quasars accrete, they vary, but there has never been an observation of a quasar or active galactic nucleus which is periodic. So what we think is happening, this is not only a star is being disrupted by a supermassive black hole, but that star got into such an orbit that it survives the encounter, comes back on eccentric orbit, and every time when it gets close, it loses roughly a mass of Jupiter. So we're seeing what we call a repeating tidal disruption event. I'm not making this up. It sounds like I'm making this up, but that's why we missed it the first time around, because we just didn't have this in our mind that such things even occur. And then Anna, to her credit, she realized what she's seeing. By now, we have Chandra time, we have Hubble Space Telescope multiple times on it, because we can now predict when the next event is going to happen, because this thing is periodic. So we have a unique event, and we can tell Hubble Space Telescope we want data that week. Hubble doesn't really, they hate so-called the target of opportunity observations, where you say, when something happens, I want you to point there, because this disrupts their schedule. But if you tell them, this will happen 5 months from now, give me time, they will, most of the time, give the time to you. So each of these is an event that has been observed in our data. And then, of course, we have Tess. So this is ASAS-SN in V-band, G-band, and Tess. And what happens is it goes up relatively quickly and decays, and then a little more than 100 days later, it does it again. And so you can do this so-called OminusC diagram. Not only is periodic, it turns out the period is getting a little bit shorter and shorter every time. So every time the orbit is modified, and eventually this star either gets too close, or at some point we have lost all the mass. So we don't have a prediction how many more of this we will see, but there should probably be at least a decade of these things happening. And so again, NASA was super happy about this. We had another press release. And we keep writing papers about it because now we can get different data. We should probably get JWST on it. It's not trivial. It's 10 to 1 oversubscribed, but nevertheless, it's a very strong, it's a very good project. And by now, we have observed more than 20 individual events. I will skip that, but what happens also, there was a fundamental change in the way we see active galactic nuclei, which is also partially caused by our project. And so there is a classification of AGN where we divide them into, as always, type 1 and type 2. We have seen AGN change type from type 1 and type 2 and then go back. And again, this is something that people did not see is happening. And now we have seen it a number of times because we're observing the whole sky and we keep our eyes open. How much more time I have? Well, all right, well, another thing that happens is that National Science Foundation spent roughly $1 billion to build this thing called IceCube, not to be confused with a well-known rapper IceCube, different thing. And it's to discover neutrinos. Neutrinos, every second, I think the number is 10 billion solar neutrinos pass through your body, but none of them interact. They just pass through your body. That's why they can pass through the sun. They're produced in the sun. They pass through everything. But now and then, there's very small chance the neutrino will interact, and especially very high-energy neutrinos, which are not produced in the core of the sun, but are produced somewhere, we actually don't know where, will interact with an ice particle. And when it does so, it produces so-called Cherenkov radiation. So the reason you need roughly a cubic kilometer of ice is that ice is transparent, and so when you have interaction of an ice particle, water particle, but in frozen form with a neutrino, you get a Cherenkov radiation beam, and you can, using these photodiodes, which are actually sunk into ice in Antarctica, so that's why you need a thick layer of ice, you can trace it back to the origin. But the positional accuracy of IceCube is only a few degrees on the side. It's very good, because it's better than anything we had. So the solar neutrinos can be traced back to our sun. We know they're coming from the sun. But the high-energy neutrinos are typically very hard to localize. So the IceCube was able to do it, and after many years, they started discovering these, and at some point, they had an event where they have seen one very particularly strong neutrino, and then they have seen a cluster of other neutrinos also coming from the same spot. And so basically, so we have the position, and then what we did and everybody else did, we pulled the data. So this is now what's called multi-messenger astrophysics, where we don't even look at photons anymore. We're actually looking at neutrinos, producing photons, but the original particle is a neutrino. But then people will look at gamma rays, optical light, across all wavelengths, and try to figure out how these neutrinos are made. And so our contribution to that was that, again, because we were just observing the whole sky all the time, we had the light curve of that particular object, and it's so-called blazar. This is where there's a jet in a quasar, and the jet is pointing towards you. So blazar will have optical light, and will have gamma rays, but also it seems, at least occasionally, a blazar will produce a super energetic neutrino that we can detect. But most of the time it doesn't, because we would have seen them. But nevertheless, we were part of that discovery, and again, NSF was very happy about that. They were mostly happy about IceCube, but also we were some part of this discovery. So comets, we are not designed at all to discover moving objects. We reject them, because moving objects are not something that we are interested in, because, I mean, they're great, but they're not part of what we are interested in. This is solar system science. So a moving object for us is something we want to detect and then reject. So the very first thing we had to do back in 2013 was we had to figure out, otherwise we would have figured literally thousands of asteroids pretending to be something else every night. So we have a software which finds them and then says, oh, that's an asteroid, don't worry about it. Occasionally software breaks and I get very excited for roughly 3 minutes, and then I figure out we couldn't possibly have that many bright supernovae. It also finds Neptune now and then. And I always like it because Neptune is saturated in our data, but it still finds it. So it's good that we can still find objects which are saturated. That means if there's a galactic supernova, we will probably actually find it, but it's not guaranteed. Nevertheless, finding Neptune always makes me happy. So we found 2 comets so far. we can only find comets if usually somebody else finds them because there are people who look for them, and if you are specialized in something, you will be better. That's just it's a basic lesson of life, that people spend thousands of hours doing something, they will be better than us because we actively not even trying to find. But this thing showed up. It showed up, comet 2017. I think what happened is it was a regular comet, it wasn't very bright, but then it broke apart and had this dramatic brightening, and it just showed up in our data. I think it was 14 magnitude. So we just discovered it because we had the data. We were not looking for it, but it was just so obviously a comet that we have seen it. And then for a month, we tried to actually have IAU name it Comet Assassin because they didn't like the name of Comet Assassin for some reason. I have no idea, no why. So they started playing these strange games, and I'm happy to say it on the camera, where they're approaching individual people in the project trying to figure out who was actually the first person who saw it because they really wanted to name it after a person. And we just kept saying, no, this is not how this project works. This is a discovery by the project. It doesn't matter who first seen it. And so eventually they did call it, so that's the official name, C2001 Assassin. Anyway, you just know, at some point it was quite bright. So here's a nice picture of Pleiades, Comet Pan-STARRS, and then Comet Assassin together. I don't think there was anything particularly interesting about it, but it was just our first comet discovery. This was very interesting. This was 2019 July. Here I am having my morning coffee. So we are mostly automated, but we still have a human, or at least a professor at Ohio State, looking at the data. And I noticed this thing, and if you look carefully, it's detected, but these dots are not aligned. So this is clearly something that it's moving, and it's moving so fast that the exposures are only separated by 100 seconds. And it's very bright. But something like that should be known by now, or it's something very interesting. We have discovered an asteroid, which is very close to us, because that's the only way for the asteroid to be changing position so quickly. And it's very bright. So there I am, caffeinated, trying to figure out where to send this information. We already went through that with the Comet Assassin 2 years earlier, but I basically forgot how to do it. Turns out you have to submit this in very specific, probably many of you actually know how to do it. They still use the Fortran you actually have to send it, if you skip a line, they reject it. Anyway, we sent this in. It turns out it was observed by our telescope in Texas and Hawaii. So not only we had one observation, we had two different observations, and they already were able to give you the distance because this thing was so close that you have a parallax to it from the fact that you're on Earth. There was an earlier observations from Brazil, so we're not discoverers, but basically with these three observations, IAU, so I sent it by noon, I think, kind of frantically asking myself why I'm doing this, but nevertheless, it seems interesting. And then they had these two observations from ASAS and one observation from Brazil. They did the orbit, and they said later that night it will pass within 80,000 kilometers of the Earth, and it's roughly 100 meters in size. We never know how big it is because it's just albedo thing, but nevertheless, if you assume standard albedo, this is a 100-meter rock, previously unknown, which is passing at 1/5 the distance of the moon. Actually was between the moon and the Earth. So I used to be on Twitter. I'm not on Twitter anymore, but I used to have there was Assassin account on Twitter, so I started tweeting about it, and then it kind of blew up. And then Australia, because they were up, they wrote a story about it, that there's a rock passing the Earth at 80,000 kilometers, a city killer, I think that people use, and we didn't even know about it. And then this really became a big story, and there were just many, many headlines. I think I did the interview on NPR, basically saying there should be professionals doing it, which they do exist. So there are two professional systems that do that. One is called Pan-STARRS, one is called Atlas, and they had it in their data, but they didn't detect it because originally it wasn't moving because it was coming towards us. Because the one that's going to hit us is moving towards us. So their software didn't see it, and we only found it by chance because by the time we saw it, the angle was such that it was already changing the angle because it was passing us. And so there's a lesson in there somewhere. The other lesson was that NASA, apparently people were extremely upset that some random people, we're not random people, but in their mind they were random people, were just not only finding these things, but also talking to the press without informing them first. That was quite a bit of fun, because what are NASA people going to do to me? Nothing. Anyway, so this was exciting. Here's the moon, here's the Earth. This thing just zoomed by. And then, of course, once it was announced, even Arecibo Observatory, which is no longer with us, they were actually able to bounce the radio off it, which is super impressive, because this thing, at some point, is moving degrees per minute. It's literally just, it has to change 180 degrees, so it's going from there to there, and at some point, it's moving many degrees per minute. So it's actually very hard to track such a thing. So that was exciting, and I never want to do this again. So this is the part where I will tell you how you want, if you want to become part of our project, or at least use our data for stuff. We make a lot of data public. So our images are not public because there's just too much data. That's a petabyte of data, roughly. If you want a particular image, you can email me, and I will probably send it to you. But I will not send you thousands of images because that's just too much. We are trying to find a way to do it, but it's extremely expensive to have a petabyte of data that can be served. But what we do serve is light curves, and we're particularly proud of this one tool where you can go on the web, type the coordinates, and that we will calculate the light curve for you. Any coordinate on the sky, you can say, give me the light curve from ASAS-SN for that coordinate, going back 3,000 days or maybe 20 days. And then a few minutes later, there will be a light curve for you can download. So this tool, which we call Sky Patrol, was just started in 2017. And there's roughly 250 papers this year using it, published. But it serves roughly, I think it's 80,000 light curves a year. So 80,000 times a year somebody goes in, because we have not robotized it because it's actually very expensive. So you have to do it by hand. 80,000 times somebody typed coordinates and retrieved the light curve. And in a few hundred cases, there was a paper using these data. But we also have pre-computed light curves for 60 million stars. And we have pre-computed light curves for 600,000 variable stars. And next year, we'll launch the next generation Sky Patrol, which will compute in real time. So Ben Shapi is running this with his student for 100 million objects. So we can feed the list and produce the light curves, but even then you can still use the other Sky Patrol if you find a new object which is not matched in the other Sky Patrol. It's a little bit complicated, but it's actually, once you go through the initial barrier, it's actually an extremely useful tool. For many years now, we have kind of almost phased it out, but this started with Isaac Cruz here when I gave this talk in 2014, because many times when we suspect there was a supernova, we actually needed collaborators, what I again called unpaid professional astronomers with bigger telescopes to take images and confirm the supernova. So this way we have done, and they have by now, I think, confirmed more than 1,000 supernovae, and they were co-authors with us on 700 telegrams.
Is that live cruise?
Yes, very much. In fact, talking to him kind of got this whole thing started, because when I gave a talk, and then I talked to him, and I said, we can identify basically the best, amateur astronomers in the world who do that, and people like Isaac. There's observatory here in Australia, which is run by a surgeon from Australia, which is 4 telescopes in the outback somewhere, and he has a telescope in New Mexico. So we're basically almost phasing out this phase of the project is almost over, but for 6 years we had this extremely active collaboration with amateur astronomers. We still have very much ongoing collaboration with AAVSO, especially there is a lot of effort now by amateurs with bigger telescopes where you can do spectroscopy. Because it turns out the bottleneck in a lot of follow-up science is there's just not that many astronomical big telescopes that can take spectra. Yes, there are 10 meters, but there's already somebody applied for time. Somebody's not going to just use their telescope to take a spectrum for you. Yes, if there's maybe the discovery of the year, they will do it. But if it's just yet another supernova, most of the time it turns out there isn't a telescope to take a spectrum. So a lot of amateur telescopes are actually big enough to take spectroscopy of at least the brightest transients that we are, and other people are discovering. And especially in some cases where there are galactic novae, sometimes we wait. Chile was shut down for quite a while because of COVID. So if there's a nova in the southern hemisphere, we didn't have telescopes to take a spectrum, but it's a 10th magnitude object. It's easily observable if you know how to do spectroscopy. The other thing that very much encourage you to look at is we have a citizen science project, which was done by, again, Tarindu and OSU undergrad, where we have uploaded 240,000 light curves on a very nice web interface, and you can just click on them and classify them. And we already used that to find 10,000 new variable stars. And by now we have, it's hard to see, but by now we have 4,000 volunteers which have classified more than 1 million, with more than 1 million classifications. But we're only half done. So there's plenty of light curves. And that's really like you can have morning coffee and just click on things. And nothing explodes, but it's quite interesting. So this is our discoveries. And then one always has to plan for the future. You probably notice the slightest possible accent that I have, very slight. And that's because I grew up in Poland, which back in the 60s, 70s, was part of the Eastern Bloc. I never visited the Soviet Union, kind of regret it. I definitely don't want to go there now. But we learn about the 5-year plans. You probably don't read the Russian very much, but the best 5-year plan is the one you can do in 4 years. It's a Soviet joke. If you're not familiar with Soviet jokes, I won't spend more time on it. But we have a 5-year plan, which we might even do in 4 years. That's what I'm trying to do. So why do we still want to keep going? One of the ways the scientists measure their impact is that we look at citations. This is like likes on Facebook, except they actually have some meaning. Because that's the reason I'm not on Twitter anymore. At some point you realize social media, but that's a whole different story. Citations are important because it means you wrote a paper, and other people, most of the time they like your paper. If they hate your paper, then they might not even cite you. Or if your paper was wrong, you might get cited for a while, but then it won't be cited anymore. So you have a sustained citations for many years. That means the paper has an impact. The benchmark number in astronomy is if your paper has 100 citations, that's pretty good. If you have 1,000, that's exceptional. I only have 2 papers. I've been doing astronomy for 30 years. I only have 2 papers with more than 1,000 citations. I have more than 100 with 100, but the 1,000 citation territory is very rare in astronomy. In medical sciences, it depends very much on the field, but in astronomy, 1,000 citations is very unusual. So one of ASAS-SN papers says now, this is my most cited paper, and this is only from 2014. And this was led by Ben Shapi, at the time graduate student. This is actually a paper I didn't tell you about, but this is about this unusual active galactic nucleus. But also, basically, we ask, when they use ASAS-SN data, we ask them to cite this paper. We never actually wrote a paper describing the project because we were too busy writing other papers. So we basically kind of a little bit cheated and asked people, just cite that paper when you use ASAS-SN data. So this paper is almost has 1,200 citations, and this is the citations as a function of a year, and it's definitely growing. So I'm not saying, you should invest in our project because you can't, but nevertheless, if this was a stock market, I would be saying, this looks pretty good. Maybe it's turning over, but I don't know. So one of the reasons we keep going is that we are definitely not done. If I start seeing this curve years from now going down, maybe we'll do something else, maybe we'll try to change the project. We will clean their clock. We can do much better than them because they only visit the same spot in the sky every 3 days, and they only cover 3,000 degrees per night. So we'll find brightest things before them, and we'll announce them. And they will discover millions of things that they will never have spectroscopy taken. So they will do science that we cannot possibly touch, but they're almost $1 billion project that will do a lot of science, but also will not do a lot of science, which is something that even professional astronomers don't realize, that we can outcompete LSST with ASAS-SN quite easily in certain areas. And we'll keep doing that. The second paper is the Sky Patrol paper. That's from 2017. And again, this is other people grabbing a light curve or 100 light curves and writing a paper, or many papers we see now is when people find a planet using Tess, they will also grab ASAS-SN light curve because they want to see the Tess light curve is only for 4 weeks, but they can see in ASAS-SN data what the star has been doing for 8 years. So for example, you can measure if there are spots on the star, you can measure the rotation period of the star, which you cannot do using Tess. And so that's, again, very much growing. And so that makes us happy. So again, these are roughly 0.1% of the most cited papers in astronomy, both of these for that given year. Then another reason we're happy is that the astronomical community, I didn't go to astronomy so I'm being liked by my colleagues. I mean, I want my colleagues to like me at OSU, but nevertheless, there are these AAS prizes, and they gave us the Tinsley Prize, which was very nice. It was a big surprise, so we're happy about this. And this year, I was giving a Guggenheim Fellowship again to think about what ASAS-SN should be doing in the next 4 or 5 years as part of the planning. So I'm formally on a sabbatical, but I am in the fall. I'm here at OSU. Another thing that will happen as we take 2 million images per year, this not only we have more images, but also the length of the data keeps growing. So now we can just do science that could never be done because nobody ever had 7,000 points spanning 10 years for an object, or 100 objects, or 1 million objects. So there is other science that we haven't even thought about, which is in our data. And either we will do it or some person somewhere in the world will say, oh, I have an idea, and then they can actually grab our data and do that. And that's happening already. So that's another reason we keep going. Finally, we have funding from Sloan Foundation and Moore Foundation to keep running until end of 2026. So if nothing else, we'll just, even if we stop doing science with ASAS-SN, we'll still run the telescopes because it's mostly automated. So there's very little extra effort for us to match our data to IceCube data, but we've been doing this. Similarly, with gravitational waves, which we finally succeeded, we do the same thing. We see the great disturbance in the force because 2 black holes have merged. And this gravitational wave passes through Earth. It's a great triumph of physics. Nobel Prize was awarded for it. It's actually fundamentally very important. We have not learned a lot of new physics in terms of traditional physics, but we're learning a lot of new astrophysics. We have seen 70 solar mass black holes merging. We didn't know such things existed. So they merge somewhere in the universe, and the wave passes through Earth, and we see that in the LIGO detector, and there's also a detector And so a lot of effort is to also find counterparts to these. There only have been one. We didn't play any role in that, but we are planning to be part of that, but we only have ever seen one, and that was 2 emerging neutron stars. When black holes merge, there are no photons. You can take 2 black holes, you release huge amounts of energy because you're literally shaking the whole universe. And yet there are no photons because there is just nothing to produce photons when you merge black holes. But when you produce neutron stars, you can release quite a bit of that energy goes into the light that we can see.
I may have missed it, but are one of the transients that you can detect lensing events of like machos and things like that?
Oh, we have quite a few microlensing events, sure. I didn't talk about it because we actually didn't write in papers, but yes, there have been papers about, so I've been focusing on the science that we did with our data, but I could give another talk, I would have to prepare it, but about science done by other people with our data, which probably would be actually a good idea, but it's
That's a way to discover, I guess, stellar mass black holes.
Yes, so there have been some, problem there, this was actually my thesis back in Bogdan Paczynski, who first suggested that microlensing could be used for that. Problem there, if we don't see the object doing the lensing, we don't know how far away it is. So all we see is the light curve. So there is the degeneracy between velocity and the times and the mass of the lens. So there are some cases where people think they have black holes, but you can never go and take more data for them. So microlensing will be good. There is a Roman space satellite being launched in 2025, which one of the core scientific missions is to see these black hole microlensing events. But we want to find stars around other black holes where we can then get more data. We can measure the mass precisely of the black hole. With microlensing, you get the statistical masses, but you don't get individual masses from the black holes. So,
with the pro-am collaboration, I remember when I started, you were using them to do like follow-up observations. You see the transient, and then
sure.
that spreadsheet, you go in there and you go
Yeah.
take the telescope and stuff. The reason reason why you're reducing that or eliminating it, is it because of the follow-up observations are no longer needed because of your pipeline that's running?
That's part of it. Part of it is that competition is not, we had few years when there was basically no competition, which is both good and bad. It makes you feel good about yourself, but it's bad because you feel good about yourself. There are now bigger telescopes at the level of $50 million. There's a telescope in California, which is a 1 meter telescope with a big camera. So they find most of our supernovae type 1a, they're mostly discovered by them before us.
Oh, okay.
So there's just basically no need for the follow-up because they're already discovered. There's another telescope, half a meter telescope, which is designed to find killer asteroids, but they also find supernovae. It's called Atlas. And so it's just part of that, there's more competition. Part of that is by now we have so many supernovae that we actually need to write papers about the supernovae we have. But there's a lot of effort in these daily, so we haven't abandoned it, but we basically scaled it down. But it was a very good thing to do, and it was great. It's just now we basically, as the field is evolving, we need to evolve with it.
No, I just had a question that's not directly related to that, but I'm truly curious. Roughly how many undergraduate, graduate fellows are in the Ohio State astronomy?
So we have graduate program, which is very strong. We have roughly 30 graduate students. Typically, they take either 5 or 6 years to graduate. So each class is 5 or 6 students. And roughly half of them, well, graduation rate is more than 90%. So our program is really exceptional in terms of people who come to OSU to get a PhD. Actually, we had one person leave in 10 years without a PhD. And that's not because we write papers for them, that's just because we create an environment that they find themselves. And they do come from, most of them are from US, but there are people, Tarindu was from Sri Lanka, I had a student from Chile, we have people from around the globe. I came to US from a different country. We like that idea that you can come here and of course it's all paid for. I mean, so as a graduate student in astronomy, we pay you. They probably would like more, but nevertheless, it's good enough. That's one good thing about Columbus. Many good things about Columbus, but cost of living makes us very competitive to many places.
I just didn't know what the size.
And then long term, roughly 50% of our graduates stay in astronomy, probably a little bit more than that. But one thing that's happening, which is probably good, is there's just so many job opportunities for people with PhDs that one of my students who just graduated left and immediately has a starting salary, more than $100,000 a year, just fresh from PhD, which we cannot match in astronomy. Just if you're a postdoc in astronomy, you will get paid maybe $60K a year, which is good enough, but it's not competitive to. Now we'll see how. Again, these are cyclical. When I was finishing grad school in '96. Internet was just getting started, and a lot of people left, and then a few years later, the internet bubble has burst. So things, but I think it's a much broader field now because, for example, the deep learning is used, machine learning is used in many different fields. So a lot of people leave because they basically know how to problem solve. But roughly half of our graduate students will stay in the field. So.
You mentioned the very small, tiny black holes that are so numerous within our galaxy.
100 million.
Is there any calculation of the density? In other words, the chance of finding one within 10 light years?
So the closest one right now is 500 light years away. And that's a fresh discovery this year.
Okay.
And that's actually from the Gaia satellite, brand new. And that's surprisingly close because if you extrapolate this, so we're working for the numbers, what it means for us, because unfortunately it wasn't us who found it, which was too bad. But again, it's good to have competition because there are smart people out there. And so we're taking the result and seeing what we can do with that. There is no black hole within 10 light years. And we're definitely not going to get hit by one. So we just say you're safe. There are no stellar collisions in the universe ever. Two stars will never, unless you live in the globular clusters, which we're not. So we're safe. I guarantee it. All right, thank you.
Any more questions?
Thank you very much.
Thank you.